This is the practice test answer key walkthrough for the test on atomic structure and nuclear chemistry. Question 1. Which value on the periodic table represents the number of protons in an element? The number of protons in an element is the atomic number. It's what defines the element. That's answer B. Which value on the periodic table represents the average number of protons and neutrons in an element? That is the atomic mass. The atomic mass is the protons plus the neutrons. The atomic number is just the protons. The chemical symbol is just the abbreviation like Ca for calcium, and the ionic charge we haven't talked about yet. Which scientist described atoms as having diffused positively charged matter containing electrons? That was the plum pudding model, which looked like this with the little electrons spread out throughout it, and then positively charged diffused matter. Okay, again, that's called the plum pudding model, and the plum pudding model was proposed by Thomson. Answer choice C. Which scientist conducted the gold foil experiment? That was the experiment with the thin piece of gold foil in the detector machine that had the alpha particles aimed at the gold foil, and some of those bounced back. This was the discovery of the nucleus, and that was done by Ernest Rutherford. Answer choice B. Which is the number of neutrons in the isotope osmium 191? Well, the first thing you need to do is look up osmium on the periodic table, and you'll see that it is atomic number 76. And 191 up here in the name, osmium 191, that's the total number of protons plus neutrons. That's the mass. Well, if you take 76 away from 91, that is 115. 76 is the number of protons. 191 minus 76 is the number of neutrons. 115 is answer A. Which is the correct name for an atom with 34 protons and 45 neutrons? Okay, again, the first thing you want to look up is what is the atomic number. Okay, the atomic number is 34. That's the number of protons in this atom, and that is selenium, number 34. So we can cross out those two because this has to be an atom of selenium. And then the name includes the name of the element and the mass number. So you have to add 34 plus 45 and find out that that's 79. Okay, so the answer is C, selenium 79. Based on the chart above, which two elements have the same mass, or two atoms have the same mass? Well, add up the protons and neutrons. For number 1, it's 19. For number 2, it's 21. For number 3, it's 19. And for number 4, it's also 19. So which two are a choice, though? 1 and 2, nope, those aren't the same. 2 and 4 are not the same. 1 and 4, those are the same. 1 and 4 are the same atom, so that's C. 2 and 3 are not the same. And in the same chart, which two are a pair of isotopes? Remember, isotopes means they have to be the same element, so they have to have the same number of protons. And when you look at the number of protons, there's only two that have the same number of protons, and that's numbers 1 and 2. Answer choice B. Okay, how many electrons are there in a neutral atom of potassium? Well, here's potassium, and you could look that up on the periodic table, and you would see that it's element number 19, which means 19 protons and 19 electrons. So that's answer choice B. The other way to do that would be to look at the mass number, which is 41, subtract the neutrons, which is 22, and you'd get 19 protons, which is also 19 electrons. So there's a couple of ways to do that. Either way, the answer is B, 19 electrons. How many neutrons are in an atom of iron according to this chart? Well, you've got 26 protons, and according to this chart, the mass number here is 56. That's the protons plus the neutrons. So if you subtract out the protons, all that's left is the neutrons, and there are 30 of them. That's answer D. Blank reactions involve the particles of the nucleus. Well, chemical equations, no, those are electrons. Oxidation reactions we haven't talked about yet. Denaturation we haven't talked about. Nuclear reactions involve the nucleus. That's answer choice C. What type of decay involves a neutron decaying into a proton and electron? So you've got a neutron that splits, gives you a proton and an electron. Well, alpha decay, no, that's 2 protons and 2 neutrons. Fission is just a general name for splitting of the atom. Decay is a general type of nuclear reaction. Beta is the type of reaction where a neutron disintegrates into a proton and an electron. Which type of radiation is the least penetrating? Well, that would be alpha. It's the biggest particle. It's the easiest one to stop. Gamma is much more penetrating. Beta is slightly more penetrating, and they are certainly not all equal. Beta particles have a mass of, well, beta particles are the same as an electron, which have, for all practical purposes, no mass. So the answer is B. Here we go. Alpha particles, we just said 2 protons plus 2 neutrons gives you a mass of 4. So the answer there is D. How does the nucleus of an atom change after alpha decay? Well, we just said alpha decay means you emit a proton, or 2 protons and 2 neutrons, which means the mass goes down by 4. And the 2 protons means that the atomic number also has to go down by 2 because you lose 2 protons, and the protons is what defines the atomic number. So that here is answer choice A. Okay, to complete the following table, you're going to need to look at your periodic table of elements. For the first one, nitrogen 14, the symbol for nitrogen is N. The atomic number of nitrogen, if you look on the periodic table, is 7, and we can jump over because 7 is also the number of protons and electrons. If we're talking about neutral atoms, the mass number, well, that's the number you're given here, 14. Average atomic mass on the periodic table, if you look it up in the book, the number they give you is 14.007. And the number of neutrons, if you look at the number of protons is 7 and the mass is 14, that means that the number of neutrons has to be 7. Atomic number 28, that's nickel on the periodic table, and in this case the mass number is 59, so it's called nickel 59, and the symbol for nickel is Ni. 28 is the atomic number again, which also means you can fill in the protons and electrons just like that. The average atomic mass on the periodic table for this is 58.693, and the neutrons is the mass number minus the number of protons, which is 31. Rb is the symbol for rubidium, and it says that the number of neutrons is 50, and if you look rubidium up on the periodic table, it's atomic number 37, which means it's got 37 protons, 37 electrons, which means the mass is the protons plus neutrons, and that's 87. So this would be rubidium 87 for the full name. And then the atomic mass on the periodic table is 85.468. And just to point out, if you look at these especially this one, this mass number and this average atomic mass do not come out to the same thing. Remember that the average atomic mass takes into account all different isotopes. So the next one has a mass number of 128 and a number of protons is 52. 52 is also the atomic number and the number of electrons. Element number 52 is tellurium, and it's got a mass of 128, so it's tellurium 128. The symbol is Te. If it's got a mass of 128 and it's got 52 protons, that means that it has 76 neutrons, and the average atomic mass on the periodic table is 127.60. Finally on this chart, tin 120. The symbol for tin is Sn, and it's atomic number 50, which means 50 protons, 50 electrons. It's number 120, that means that's the mass number. Average atomic mass for tin is 118.7. It's actually 710. And then if you take 120 and remove the 50 protons, that means there have to be 70 neutrons. Okay, so protons, electrons, and atomic number are all equal. Mass number is protons plus neutrons. The number of neutrons is mass minus protons. And the atomic mass, the name, and the symbol all come from the periodic table. Calculate the average atomic mass of the following based on the percent abundance. So remember, for these you're going to take the mass and multiply it by the percent abundance, which you have to put into a decimal. So 0.05845 for the first one. The second one is going to be times 0.91754, and then times 0.02119. When you do those out, you find out that the contribution for Fe54 is 3.15 0.2770497. For isotope 56, it's 51.322546668. And for isotope 57 of iron, that's Fe, comes out to 1.2064611105. Okay, when you add all that up, you get a mass of 55.68177.828. But we have to take into account significant figures. We have four significant figures here for multiplying. So we're going to round to 4 significant figures, which would be 55.68 AMU. So remember, when you're doing this, you take each isotope's contribution, you multiply the mass times the percentage, and then you add them all together here, and then round according to the number of significant figures. Write the symbol for the isotope of iron with 31 neutrons. Well, iron has the symbol Fe, and its atomic number 26, so that's the number that goes on the bottom. And if it's got 26 protons and it's got 31 neutrons, 31 plus 26 gives you 57. So that means the mass number on the top is 57. Write the equation for the beta decay of gold 198. Okay, so we look up the symbol for gold. It's Au. 198 is the mass that we're given here. 98. And gold is atomic number 79. So this is beta decay. In beta decay, remember, you've got a neutron which turns into a proton, so the number of protons goes up by 1. But because neutrons and protons have the same mass, the mass number overall doesn't change at all, because you're swapping two things that have equal mass. But I've changed the atomic number, which means I have to look up the new element. Number 80 is Hg, mercury. And then there's also a beta particle that goes along with that. Equation for alpha decay of uranium-233. Look up uranium on the periodic table, you'll see it's number 92. Okay, in alpha decay, the alpha particle splits off from the rest of the atom. Alpha particle has a atomic number of 2 and a mass of 4. So that means you have to take away that mass and that number of protons from the starting element. So 233 minus 4 brings it down to 229. 92 minus 2 is 90. Look up element number 90 on the periodic table. That's thorium. So you always take 4 from the top, 2 from the bottom, and you have to find the new element. And then the other part is always that 42He for alpha decay. Okay, another alpha decay, and this time it's francium-220. Look up francium on the periodic table, and you will find that it is element number 87. Okay, so again, we're going to take that 42He and we're going to subtract it from the starting element or isotope, which means the mass goes down to 216, the atomic number goes down to 85, and that element is astatine, which has a symbol At. Okay, beta decay equation for potassium. Potassium is a symbol K, and it's potassium 42. Look up periodic table, it's element number 19. Remember, beta decay, you're adding a proton and taking away a neutron. So you increase the atomic number, you do not change the mass, and you have to look up that new element, which in this case is calcium, and then there's always the beta particle that goes with it. Okay, so the formula for half-life is the amount remaining is equal to the amount that you start with multiplied by 1/2 raised to the power of the time elapsed divided by the time of 1 half-life. So in this case, the starting amount is 150, and that's times 1/2 to the power of 365 days, that's 1 year, over 27.7 days. So that means 150 times 1/2 to the power of 13.18, which comes out to 0.016 grams. The half-life of tin 117 is 14 days. How much was originally present of a sample is if 25.44 grams of a sample is left after 34 days? Okay, so this time we've got the remaining amount, 25.44, and we're trying to solve for n0, so that's times 1/2 to the power of 34 days elapsed, and the half-life is 14 days. So 25.44 grams, so that's 1/2 to the power of 2.49. So 25.44 grams equals the starting amount times 0.178. So now to get back to the starting amount, we have to divide both sides by 0.178. And then we get N0 is equal to 142.9 grams. The half-life of technetium is 6 hours. How long would it take a 100-gram sample to decay to 6.25 grams? Well, so we really want to figure out is how many half-lives have to go by from 100 down to 6.25. Well, if I start with 100, that's at 0. After 1 half-life, I'd have 50. After 2 half-lives, I'd have 25. 3 half-lives is 12.5. 4 half-lives gets me down to 6.25 grams. Okay, so 4 half-lives have gone by. That's not the answer. The answer is 4 half-lives times 6 hours for each half-life means 24 hours have gone by. Okay, if the half-life of nitrogen-16 is 7.2 seconds, 36.7 milligram sample decays over 2.5 minutes. How much of the sample remains? So, trying to find the remaining amount, we start with 36.7 milligrams times 1/2 to the power of, and it's 2.5 minutes. If we convert that to seconds, it's 150 seconds divided by 7.2. Seconds is the half-life. So 36.7 milligrams times 1/2 to the power of 20.8, which means you're going to end up with 2.01 times 10 to the -5 milligrams. Okay, oldies but goodies. Complete the following calculation. Well, if you multiply 0.00012 times 4701, you would get 0.056412. But if we look at the numbers up here, this has 2 significant figures and this has 4. Since we're multiplying, we go with the smaller number of total significant figures, which is 2. So I have to go first significant digit, second significant digit, round off at that point. You get 0.056. That is your answer. So 402 meters over 1 times millimeters is what we're converting to, so that goes on the top, meters goes on the bottom. 1 millimeter is equal to 0.001 meters, so 402 times 1 over 001 is 402,000 millimeters. How many significant figures do each of the following numbers contain? Well, I've got 2 digits and then I've got 4 zeros sandwiched in between. Sandwich zeros count, so that's 1, 2, 3, 4, 5, 6 significant figures there. And in this case, I've got a couple of zeros to the left in a decimal number. Those are not significant. I've got 1, 2, 3, 4 digits, a sandwich zero, that's 5 digits, and then a trailing zero. All zeros trailing in a decimal number count. So that gives me another total of 6 significant figures. Don't forget that you can check out the Socrative additional practice problems. It's room number 299336. There's a link to that, and the number is also on the home page.